Good afternoon, everyone. So let's get back to our discussion of gradient descent. See, I don't know why this screen just turned off. Okay, it's back. All right. So last time, one of the more important things we did is we talked about this gradient descent algorithm. The idea here is to find a minimum or particular local minimum. We start with random initialization, and then we take small steps downhill, and we prove that if the step size, alpha k, is small enough, then we should eventually, we will keep decreasing our cost, and our goal is this way to get to the bottom. So this is, the algorithm is, you can just repeat this line over and over again. It's as simple as that. We basically take our old location, we subtract some scaled version of the gradient, evaluate it at the old location, and that becomes the new location. Okay, so we did a bit of analysis, which we'll come back to today. So we started with this Taylor series expansion, stated here for generic W. Then we plugged in the version of W after the step, and we got this. And then we said, well, when we do gradient descent, we know that the difference between the new and the old step is this minus alpha k times the gradient. So we plugged that into those expressions, and we got this. And then finally, we pulled this gradient norm squared out of the order term, just so that we could do a direct comparison of this negative alpha k and this one. They're both multiplying this positive quantity. What we hope happens in gradient descent is we hope that the new cost is smaller than the old cost, which means we hope that all of this is negative. And we see that this is taking us in the good direction. This is taking us in the bad direction because it's positive. And so we want that this term overwhelms this term. And this does happen. We know that by the definition of this order, this means that this term is bounded above by some constant c times alpha k squared. And when we think of making alpha k really small, no matter what c is, we can find some alpha k for which this term is greater in magnitude than this term. And since this is negative and this is positive, this negative will overwhelm it, and we will have a decrease in our cost. So that's why this method, gradient descent, works for small enough step sizes. So today we'll talk about a specific algorithm called the Armijo rule, which will allow us to vary this on the fly, and is based on this idea here. Okay, so that's what we did last time. And then we were basically applying this to the cross entropy loss, which is the loss that we see in logistic regression, in particular binary logistic regression here. So we basically want to minimize this. And so our approach with gradient descent is we initialize W randomly, and then we compute gradients. We go downhill, downhill, downhill. And so our main task then is to compute gradients of this. We'd like to do this efficiently, and then we're going to talk about how to code it in Python. So when working with costs of this form, we can exploit the fact that there's a certain structure to them where we notice that the cost is the sum over the training samples of terms that depend only on a single training sample. Those terms depend on z. So we can say that this is a separable cost, meaning that if we call this thing f of z, that f of z is the sum over I of fi of zi, where these are the zi's, and then this is the function fi. That function does change over I because it depends on the training sample targets yi, and those do change over I. Okay, so this part is pretty easy to deal with when we think about it in terms of the z's. And then the next question is, how do the w's relate to the z's? Well, we can think of w as relating to the z through this equation. This is what happens at a specific I. But if we stack all those i's into a column vector, then this becomes the A matrix. So this is how we relate w to the z's. So finally, we have a two-step process. We take in w, we can compute the z's from w, and then once we have the z's, we can compute this function here, which we call f of z. And if we compose them, we first, take w to z and then z to f. That is how we can think of J, two-step process. We would like to exploit these two steps for computation of our gradient, and we do this through something called the multivariable chain rule. So the idea is we have w going to z going to f. So what we can do is df dwj, we can write as df dzi times dzi dwj, summed over all the different i's in this function. So we can sort of think about this more intuitively like this. There's some function f, which we know depends on all the zi's, but each of those zi's depends on all the wj's. And so when we think about how a particular wj affects f, we see that it affects it going through all these different zi's. So there's like many paths that take wj to f, many of these parallel paths. And so when we compute the gradient of f with respect to wj, we can sum the gradients over all those different paths. That is what the multivariable chain rule says that we can do. Okay, so that's kind of the hard stuff. Everything else is just going through the computations for how we do this. Are there any questions on the big picture about the two-step decomposition here, or about the multivariable chain rule? Yeah.
So the J function is, where is that coming from?
So J is this. So J is when we define J, we're defining this in terms of the W's. Okay, but if I want to talk about this in terms of the Z's, I can't use J anymore. J is what I use when I want to say, how do I go from the W's to the F's? I have a different function that takes me from the Z's to the F, and I call that f of z. Does that make sense? I can't use the same notation because really the function f of z is different than the function j of w. Right? Like just from this picture, f of z takes you from here to here, and then j of w takes you from here all the way to here.
Aren't they almost the same thing? Because we're not doing any other computation on the f of z to get j.
It's just more like a notation thing. I don't want to use the same notation to mean different things. If I define a function j, which is in terms of the w's, I don't want to define j also in terms of z's, because it could be very confusing. You don't really know how the function's defined. So, but you're right, at the end of the day, the quantity is the same. It's this thing. But if I think about it in terms of z's, then it's this function. Whereas if I think about it in terms of w's, then it's this whole thing, which also includes this. Okay. So another question?
It's just the stuff we did on Monday.
Yes, just reviewing, we got to, I think we got to the end of this page here. Okay, any other questions? Okay, so basically now that we have this approach, this is sort of a structured way to break up this big computation, this big gradient computation, into two relatively simple gradient computations. So the first one is df dzi. So if I want to know, what's the gradient of this with respect to a particular zi, then I don't have to worry about all the I in the sum. I can just focus on the one that I'm interested in. And then I just do d of this expression dzi, which is pretty straightforward. So we do the first term, d this dzi, so we use the chain rule. So from the log, we get 1 over that argument. That gives us this. And then we have to look inside and take d dzi of this. But the way that, the 1 doesn't matter, and then the way this works, d dzi of that is just that itself, ezi. So that's the d dzi of the first term. D dzi of the second term is just minus yi. And then we can write this a little simpler. We can multiply top and bottom by e to the minus zi, and we get this. So this is our most efficient expression for df dzi. It requires only one evaluation of an exponential term. Those terms are kind of expensive when you compute them because it actually involves a lookup table. And so these are the sort of terms we don't want to evaluate a lot of those if we can evaluate fewer. Okay, so this is something that we'll eventually code. And then the other term, dzi dwj, we can look at this, and we can maybe, because this is a vector matrix expression, we can break this up into, let's just look at the ith component here, which requires us to look at the ith row here times this, and then we get this expression. And now if I do dzi dwj, you can see that I'm just going to focus on one of the wj's so I can forget about all the others. And then when I do the partial derivative of this with respect to wj, I just get aij. Okay, so finally we have the two ingredients here, and we can just plug them in, and we have that expression for df dwj. Okay, any questions on that? Okay, so when we do this stuff, usually we don't only want to compute the gradient, we also want to compute the cost. And for example, we may want to monitor the cost and see how much the cost is decreasing to know if we're running gradient descent, how many iterations we have to run it for. If it looks like things have stabilized and things are not changing, we can stop. But if it looks like the cost is still decreasing, then we should probably use more iterations. So in order to determine that, we want to monitor the cost, and then of course we need the gradient to do our gradient descent. So we typically do both these together. And the way that we structure this is we structure this in what's called the forward pass and the backward pass. The backward pass is where we compute all our gradients, and the forward pass is where we compute all the stuff we need for our gradients as well as the cost. The reason that we use these terms forward and backward pass will become more evident in Unit 8 when we talk about backpropagation, but for now, they're just names we're going to call these steps. Okay, so again, in the forward pass, you can say that our goal is to compute the cost. So what are all the things we have to do to compute the cost? Okay, so first of all, given the w's, we have to compute the z's. We can do this with just a matrix multiply. Now that we have the z's, we can we want to evaluate this expression here. And then eventually sum this to get f of z. Okay, but what we would like to do is we don't want to compute, see there's one exponential here, and I'm computing one here too. Is there some way that I can maybe change this a little bit so that I can compute this once and then use it for both expressions? So that's our goal, is to try to be a little bit more efficient. Okay, so this is our fi. The question is, can we rewrite this in terms of this quantity here that we're using in our gradient? The answer is yes, so let's see how we do this. So the first thing we can do is remember that if I put a minus in front of the log, that's like inverting its argument, right? And then the second thing we can do, that's where we get this. Now, there's also in the numerator, there's this e to the zi here. So how did that appear? So if you think about this, you can write this as minus log of the numerator and then minus log of the denominator, which gives this. So the minus log of the numerator, well, what you see here is that the log and the exponential cancel, and you just get minus zi. So it's like we're adding a minus zi here. So to cancel that, we also add a plus zi. Okay, so this term is canceled by this term. And now that we have this, you can see we can rewrite this as this, and we can take advantage of the fact that this these guys are computed, we can compute them once, and then we can use them both in this expression and in this expression here. So that's why we're going to all this work to rewrite this. Okay, so finally, once we have these FIs, we just sum them to get our f of z, which is the same thing as j of w. And then the backward pass, this is what we got from the previous page. We plugged in these expressions into here, and we get this. But when we program this, we don't want to have a for loop to implement this sum. We want to do this with matrix vector multiplies. So we just have to rewrite this expression as a matrix vector multiply. So for that, we can realize that on the left side, this is the jth component of the gradient of j. Right? So this is like the jth component of this vector. On the right side, we can notice that this is the ith component of the gradient of f. So because f is defined as a function of z, when we take the gradient, that's the partial derivatives of the different z's, and the ith one is this. Okay, so you can see this is the jth argument of this matrix, this is the this vector, this is the ith argument of this. And so now vector, vector, we can see there's a matrix here, so what exactly happens? Well, there's one little annoyance, which is that if this vector is indexed by I, we'd like this matrix to be indexed by I over its columns and over j over its rows. But the problem is it's actually swapped. So we have to reverse the order of these, and we can do that by transposing the matrix. So finally what we get is this expression. This is A transpose times the gradient of f equals the gradient of j. Okay, so it's kind of stuff you saw back in homework 0. All right, so essentially, so now we have everything we need. We just have to program this stuff. And before we do that, are there any questions on anything here in the derivation? Okay, so let's see how we program this. So we want to build a function that takes in w, which is our current value of the parameters, as well as the training data x and y. And so the first thing we need to do is we want to build this A matrix. In order to build that A matrix, we're going to basically stack some 1s next to the X matrix that we took in. These are the training features. But we need to know how long to make that 1s vector. So for that, we have to figure out how many samples we have, and we can do that by extracting the first dimension of X. So that gives us n. Then we can make this 1s vector. Then we can do the column stack to get the A matrix. Once we have that A matrix, we can execute this with just a.w. It gives us our z vector. And then this term inside the log that we see we want to use a couple places, we can create that using that vector z just by doing 1 divided by 1 plus numpy exponential minus z. So here numpy is doing this broadcasting where it's smart enough to realize that even though these operations are defined for scalars, that it can just do that for every element of the z vector. So it will create a py vector, which is essentially the vector of this over the different i's. And if you remember, the reason we call that py is because in the logistic model, this quantity is actually the probability that the training sample yi equals 1 given that value of zi. So that's why it's called py. Okay, so once we have that py vector, we just need to compute this. So we can take the minus log of the py vector here, and then we want to do this. And so here again, we want to do a pointwise multiply between these yi and zi vectors. So whereas in MATLAB you'd use a dot star, in Python you just use the star alone, and it knows to do a pointwise multiply. So that's another one of these Python broadcasting rules. So finally, this gives us this term over here. And that gives us, and then we sum across that vector to implement this sum, and then we get j. Okay, so that's our cost. Now what about our gradient? So since we already have computed this term, called it py, we can just do py minus y to get df dz, this term. And then the last step is we just need to do a matrix vector multiply. And so to get the transpose, you can just do a dot t, that transposes the matrix. And then for that new matrix, you use the dot function to do this matrix multiply. So that will give you this vector over here. And those are the terms we return, or the cost and the gradient vector. Okay, so that's one way we can implement this in Python. All right, any questions on that? Okay, hopefully it's pretty straightforward. So there's a few other options we have in terms of the implementation. So this is from the previous page, the same thing. This is like a function that takes in W and the training quantities. But when we run gradient descent, in some cases it's sometimes more useful just to have a function that depends only on W, that doesn't depend also on the training quantities. And so one way to do that in Python is to use what's called a lambda function. And a lambda function is the same thing as an anonymous function in MATLAB. Basically, it's a way that you can take a function of several things, here w, x, y, and you can fix some of those inputs and have it still remain a function of a selected one. So here you're saying this new function jeval will be a function of only w, and the function is defined as this. So here w is the free variable, and then these quantities are going to be fixed at the training data. So what you get out of here is you just get a function only of w. So it's just sort of like you're wrapping this more generic function inside another function that fixes the training data and leaves w as the free variables. So for a given vector w0, if you want to evaluate the cost and the gradient, then we just call jeval at w0 and it puts out the cost and the gradient. Okay, so this is it's kind of a minor thing, but these lambda functions are pretty useful. Okay, any questions on that? All right, so there's another option that's a little bit more involved, but it's also much more powerful, and it's something that we'll see a lot more of. And this is building what's called a class. This is an example of object-oriented programming. So here, we build this class thing, and the class is going to be a collection of functions as well as some internally stored data. So a class must always have an initialization function init. So you always have to have that, and then you can have as many additional functions in your class as you want. So what the initialization function does is when you first instantiate this class or this object, it calls this initialization function, and it does it just once. So this is all the setup. And once that's set up, then when you can call these functions, it's going to rely on all the stuff that you set up in the initialization. So here's how it looks. When we instantiate the class, we say logistic fung, and we give it the training data, and then it gives us this object here, which has data inside it. In particular, we've stored our training data inside there, but it also has functions like jeval as something part of this object. So like later we can do logfun.jeval, and then it's going to call this. And here this is just going to be a function of w only. Okay, so what we did in this initialization function is this guy takes in the training data, and the first thing we do is we save that as internal variables. So when you see self.x, that means you're declaring a variable that's always going to be part of a logistic function, and you're just, you're making it equal to x. So this is your way of sort of remembering the values that you passed in. And later when you're executing this function, if you want to use like y, you do self.y, and then it knows to look internally for that variable that you set up over here. Okay, so that's one thing we're doing. Another thing we're doing is we're going to create our A matrix, and we're going to store that as an internal variable. And so we're doing that just like we did before. We get the number of training samples, and then we do this column stack with the ones vector of length n. in our training data X, and we're storing that internally as self.a. So now we never have to recompute that. That's always going to be stored as part of our model. So when we come to our JEval function, this is very much like what we did before, but some of this stuff we take out because that stuff was already done during initialization. So now we can just focus on computing z as self.a.w, and we can do py just like before. We can do j, where again we're going to use self.y, because notice we're not passing in a or y here. Those are actually internal variables inside this class, this object. Okay, and then finally we return these, and so when we call this logfunc.jeval, it prints this out. So this is how a lot of those scikit-learn functions that you've been working with are implemented, like those methods for logistic regression. You know, they have like a fit function, which takes in your data and computes the beta parameters, and then they have a predict function, which takes the parameters and some new test features and applies the parameters and makes a prediction and so on. So if you want to add additional functions, you can just add as many as you want. All right. So I think you guys have all seen this stuff in some of your early programming classes. So hopefully this is not too unfamiliar. All right. Are there any questions on anything here? Everybody good? Okay. All right. So I highly recommend whenever you program a routine that computes the gradient to test it, because it's easy to mess up. Maybe you derived it, maybe there's a mistake in your derivation, or maybe there's a mistake in your coding, especially when you're using Python broadcasting, maybe you're not familiar with it. And there's a really easy way of testing things. It's based on this idea. Remember, this down here is our linear approximation, and we know that this holds accurately whenever W0 and W1 are close together. So the idea is that if this is true, which we can force it to be true by making these close together, then we can move this W0 to the other side to get this approximation. And this is something we can use to test our implementation. So essentially, you randomly choose W0 and W1 that are close together, and then you compute this on one hand. On the other hand, you compute this, and you check to make sure that those are almost exactly equal. And if they are almost exactly equal for randomly chosen W0 and W1, it's very likely that your implementation is correct. If they're not very close, then something is wrong. Go back and figure it out before you start using this function. So I highly recommend this on Lab 6. Lab 6, you're going to have to derive some gradient stuff on your own, similar to a homework problem. Then you're going to have to implement it, similar to this stuff. And then eventually you'll use it. But before you use it, make sure you test it. Make sure everything is working according to this. Okay, so let's see how we do this. So first we have to generate these random vectors, W0, W1. So we have to figure out, first of all, how long are they? How many features are there? So we can get that from the second dimension in X. And then we'll just draw W0 as a zero mean unit variance Gaussian random vector, IID, of the correct dimension. And then to compute W1, we'll start with W0 and we'll add a very small perturbation. The perturbation is a small step size. Here it's 1e minus 6 times another random vector. So this is sort of like moving in a random direction away from W0. So now we have these two vectors, W1 and W0. We can compute this quantity, JW1, as well as the gradient at W1. We can also compute JW0 as well as the gradient at W0. So that's what we're doing in these two steps. And once we have those, we can look at the predicted, DJ predicted is basically this. And then we can look at the actual difference between the two J's, which we can compute here. And here we're printing out the value of the difference and the predicted difference, and you can see that they're accurate to 5 decimal points, or 5 significant precision of 5. If you would print out more digits, then eventually they would start to differ. because W0 and W1 are not exactly, they're a little different, and because the function is not exactly linear. So this is just an approximation, but we want to make sure that the approximation is still pretty good if you use a small step size, as you can see here. So this is just a check. Gives us some confidence in our implementation, so now we can move on to actually program gradient descent. All right. Good so far? Okay. All right, so gradient descent is really easy to program. Remember that essentially we just call essentially this expression over and over again. This is our old point, the gradient at our old point, minus a small step size or learning rate, and we just basically are overwriting the point. So this is the old one with the step size. We're just overwriting that value, and that becomes the new one. And this is just in a for loop. So every time we go through the for loop, we're at the old point, we're evaluating the gradient and the cost. We're using the gradient to take our gradient descent step. And then we're going to save the history just so that we can use this for debugging. We're going to append the cost and append the parameters W0 in these structures. And then finally, we'll convert them to NumPy arrays because it's easier to work in NumPy. You can do that with this. And so this is just a simple gradient descent function that takes in the function JEval that we use to compute the cost and gradient, the initialization, and then it takes in the learning rate, which will default to 1e minus 3, and the number of iterations to use in the algorithm, which will default to 1,000. Okay, so gradient descent is pretty easy to implement. Any questions on this? All right, so we have everything we need. Let's see how well this works. So, so we're going to initialize randomly. So we have a Gaussian of the right dimension, and let's see. So okay, so we're just making up a shorter name. This is our class log function .jeval. We're just making up a shorter name for that, calling it jeval. We're going to select 2,000 iterations and a learning rate or step size of 1e minus 4. And then we call the function on the previous page with this jeval with our initialization up here, with our learning rate and the number of iterations. And that will run gradient descent, and it will report the final parameter vector W, as well as the trajectory of all the costs over the iterations. Oh, actually, no, this is the final parameters, the final cost, and then the history contains both the costs and the parameter values over the iterations. So, okay, on the left, this should say 2,000 iterations, not 1,000. But we're running this for 2,000 iterations, and here we're plotting the loss or the cost as a function of iteration. Notice that we're doing this on a log-log scale. This usually makes the plots much more interpretable to plot iterations on a log scale, and often the loss too on a log scale. So you can see essentially that what's happening is as we go through our iterations, the loss is decreasing, which is exactly what we want to happen. But even after 2,000 iterations, it still seems to be decreasing. Basically, it's taking a while to optimize this. And this is because, so convergence is slow. This is because gradient descent is just the simplest, most primitive technique. We can definitely do better. And in fact, one of the issues with the gradient descent is you have to carefully choose this learning rate. If we know that the learning rate should be, if it's small enough, it will eventually converge. Well, how small is small enough? That's hard to say. It depends on the function we're working with, depends on where you initialize. So, one way is you can just try a bunch of different step sizes, and you can plot what happens to try to get a sense of what the best step size is. And that's what we're doing for now. And then later on, we'll talk about a more, a fancier algorithm that will adjust the step size with every iteration. in any case, so this is what happened with the loss over the iterations. But we can also look at the final iteration, the final weights. We can use them in our classification experiment. So we're making this prediction function, which will take the intercept, W0, it pulls out the intercept, then it takes the rest of the weights and applies them to the training samples. Actually, it just applies them trainer or test, whatever matrix we give it. And then this gives us our scores. And finally, we do a quantization of those scores where if the score is positive, we say y hat is 1. And if the score is not positive, we say y hat equals 0. And we can just convert with these round parentheses, we can convert that. This is like a logical value, basically. Converts that into a true false. And so this will report the final y hat that you get from those x's and those parameters. So we can use that in this case where we look at the test features and we can get our test predictions, and then we can look at, on average, how often is it that the prediction equals the true labels, and that gives us the accuracy, which ends up being 96.8%, which sounds good, but it's not as good as we could do. We could do better. And for example, maybe if we let this run longer, we could train a better classifier. Because so far, we're not actually minimizing the logistic regression or the cross entropy loss, right? We're on the way of minimizing it, but we're not quite done yet, and so the weights are suboptimal. Okay, so let's do this little experiment. We'll try 4 different learning rates. The one we saw on the previous page was this orange line. Now, if we use a smaller learning rate, smaller by a factor of 10, you can see that it converges even slower. That's the blue one. If we increase it by a factor of 10, we get the green one, and you can see what happens with the green one is the cost is not decreasing in every iteration. Like in the first couple iterations, it actually increases. It's overshooting. It's maybe going in the right direction, but it's overshooting the minima and actually landing farther away than, or at a higher cost than originally. And then somehow it recovers and it does well, but then it increases again and it recovers and it kind of oscillates. Eventually, it seems to do a pretty good job, and it's the best of all 4 step sizes, but it might be a little disturbing. We don't really know if it will always converge because obviously it's diverging for a few iterations. And then we can say, well, if that was good, maybe we should make the learning rate even larger. So if we just double that last value, then we get this red trace, and you can see things are really kind of going crazy and oscillating where it's getting really bad and then doing good and so on. And eventually it's not even converging. It seems like it's not actually converging to the minimum of the cost. So here are the corresponding test accuracies. You can see that in the best case, we were getting up to 98.9%. But what's clear here is that the learning rate is important, and it's not obvious how to best set it. So that's our objective going forward. Are there any questions on anything so far? Yeah.
In the green one, although it does sort of converge at the end, shouldn't we just stop? Wouldn't we just stop seeing that it's going sort of up? I mean, starting it as the cost function is increasing. So wouldn't it just decide to stop it and not go any further?
Well, then you would be stopping at this value, which is much worse than this value.
I mean, how do we show the faith that it is going to converge at one point? Now that we know this, so we sort of went along, but then if we did not know, how would we decide to show faith and actually go along with all the points?
Well, we'll talk about an algorithm next that will do that. But I think that maybe the more important question is, in practice, if somebody gives you a cost function that's non-convex, a cost function where maybe there's multiple minima or you just don't know much about it, it's actually very difficult to really know what the best step size is. And it's not unexpected that you will maybe go up and then go down and so on. Like when you work with deep networks, we'll talk about a couple chapters. Those have very complicated cost functions where there's like many local minima, and this is just expected behavior. You hope to go out of some shallow local minima, and then maybe we're in a shallow one, and then we converge to a deeper one, and so on. And so when it's convex, then we don't want to see this behavior. We know that we really should be getting better every iteration. But when it's non-convex, this is actually typical behavior, like that green curve.
So how do you know where to stop then? How do you know where you come across a minimum? If you just keep going across and going down and down.
Yeah, it's a great question. So what you do is use cross-validation. So you have your training set, and then you have your validation set, or test set. So you use your training data to do this, and this would be your training loss. But separately, you compute your validation loss. And the validation loss is much more believable than the training loss, right? And the validation loss can give you a sense of when it's a good time to stop. So maybe the validation loss goes down and then eventually goes up again. That can happen. At that point, you say, okay, I should stop when that validation loss was at its lowest point. So that's a common technique. Yeah. Okay. All right. Any other questions here about step sizes? All right. This chapter is really focusing on techniques where we really just want to do everything we can to converge, which is the right framework for convex optimization. But later on, when we get to neural networks, we'll talk a little bit more about techniques where we don't expect that the cost function should get better in every iteration, and then we'll have to use a different set of algorithms and so on. Okay, so now we can talk about this approach to adapting our step size. This is just one approach of many that could be used. It's a pretty famous one, and it's taught in a lot of basic optimization courses called the Armijo approach. So to understand this, we come back to this result that we got in our gradient descent analysis a few slides back. And here what we're doing is we're rewriting things with a notation that just makes the step size explicit. So again, this is going to be the cost after the update, written in terms of the cost before the update, and a term here that is linear in alpha k, and then a term here that is quadratic in alpha k, or maybe even higher order. So this is what we were looking at before, and this is how we justified that if alpha k was small enough, this term should overwhelm this term, and we should make progress in decreasing our cost. Okay, so this is how the Armijo rule works. First, we're going to choose some number, and it can be any number. It's going to be called C. It could be any number between 0 and 1. And let's just think about it being chosen as 0.5. What we do then is at every iteration, we have some guess of what the step size should be, alpha k, and we check to see if this inequality is satisfied. So when you compare this to the above expression, say first of all, this term is missing, and second of all, the C has been inserted over there. Otherwise, it looks just like this. Okay. So in order to understand what's going on here, I think it helps to look at a picture. So this is the picture. This is this cost at the updated parameters as a function of the step size. So imagine that you could do an experiment where you use many different step sizes. What you would notice is that the cost looks kind of like this. So remember that when alpha k, the step size, is very small, okay, when alpha k is very small, then this quadratic term is tiny, and we can ignore it. So for very small alpha, we can focus on this, and you can see that the cost has a linear dependence on alpha. Basically, this is the slope. Negative, this is the slope, right? So when you look at this picture, in this region over here, for very small alpha, this function, j, is approximately linear around the origin. And this dashed line shows exactly that linear approximation. It just shows this term. Okay. But what happens is, as alpha k gets larger and larger, then actually this term will eventually dominate. So let's say if alpha k is greater than 1, then this is going to be much greater than 1, and this is small. So eventually, you might get like a quadratic or even a higher order behavior. So that's why this goes up. And here you can see the problem. Basically, this height here is the height where we started. This is the cost where we started. And you can see that if alpha k is too large, the cost after the update is actually worse. It's higher than the cost where we started. So we definitely don't want to be doing this because we're actually making negative progress. We would like to be, ideally we'd like to choose alpha in this range because this makes the most progress possible. This would be the optimum step size, somewhere around here. And so what the Armijo rule does, remember that it looks at c times that slope. So that's what the blue line shows. This is in the case where c is 1/2. So this blue line is half the slope of this dashed line. So what the Armijo rule says is you take a step, which means you know the value of this. So you have a certain alpha in mind. Maybe this is your alpha. You take a step, so you compute this. So you compute this quantity here, and you check, is this under the blue line? If yes, you call the step successful, and you move on to the next step. If, on the other hand, maybe you tried this step size and you got this cost. Now, since this cost is above the blue line, you say that's unsuccessful. I'm not going to trust it. I'm going to go back and do the step again, but with a smaller alpha. Okay. So that's how the Armijo rule works. And basically, because the Armijo rule guarantees that you will make a certain amount of progress in terms of minimizing your cost at every iteration. Right? You will always be, hold on one second, you will always be below this blue line. And so the place at which the largest possible alpha that you can use is where this red curve is just touching the blue line. So all the admissible alpha, according to this Armijo rule, are in this range here. Any of those alpha will work. They'll allow you to take a successful step. But any larger alpha, it will be a failure for the Armijo rule, and it will say, sorry, do it over again. So now that you can see that this parameter c, there's many different c's that can work. Like this was c equals 0.5. This means that these are the admissible alpha, which means that anything in this range can happen. If you would have used a smaller number here, like 0.1, then this would have been the line, and your admissible range would have been here, which is larger. So there's a greater chance that you'll accept the step, but you have these solutions here which may not be as good. You may not make much progress here in terms of decreasing the cost. On the other hand, you could use C that's closer to 1, and then you have something like this, and now maybe there's only a very small range of alpha. So there's sort of a trade-off in how you choose that C parameter. I don't think there's any optimal way of setting it. It's just sort of a heuristic design parameter, and so 0.5 is maybe a good starting value. Okay. Still have a question?
Yeah, so is C it's just something you choose?
You choose it. Yeah, so it's just something you choose, and then it's kind of part of how you parameterize this algorithm.
Is there no way to solve for the best C for the current set of W's that you have?
That's a good question. So there's another approach that we can think about called line search. So the idea here is that at every iteration, you just try a bunch of different step sizes. So maybe you try a grid of step sizes, and what that would mean is you would end up taking those different steps and computing all these different costs. And once you do that, you could just look through and figure out what is the best step, right? So in this case, maybe you would say, oh, this was the best step. That would be more precise in terms of finding the best step, but you've wasted a lot of computation to find that one step. So if I've taken 10 different hypotheses of what my step could be, then only 1/10 of my computations will actually be useful in taking a step. I will be wasting 90% of them trying to find that perfect step size. Whereas the Armijo rule is trying to be efficient. It's just going to take a step, and if it works, great. We've made progress. If it doesn't, it's going to say, okay, I'll try again, but maybe I'll make my step size small enough that I'm pretty sure the next time it will work. And it tries to avoid a lot of unnecessary gradient computations and cost computations. Because remember, every step you take, you have to essentially run your code, like you have to run this piece of code, which looks at all your training samples and does all these computations. And that could be, if you have a big training set, that could be a significant amount of time. So the Armijo rule there's nothing optimal about it. It's just a pretty practical technique, pretty efficient if you can find a good value of C, basically. And there are many other approaches. This is just one relatively simple approach that we can talk about, and it's pretty common to talk about this in optimization courses.
You said you run it, and if it fits within, underneath that blue line.
Yeah. So when you basically you have a step size in mind, you take a step which tells you, this value, which tells you, gives you one sample in the red line. And then this blue line you can get without much computation at all, because for the blue line, you've already computed this, you've already computed this. So any point on the blue line is very easy to compute.
Does the red line change, or is there no reason you can't just look at the intersection of your line and pick that alpha?
Yeah, so anytime you want to compute a point on the red line, you actually have to compute
Oh, you have to run
this.
both.
Yeah, you have to do your full cost evaluation. So that's why it's expensive. Okay, so a couple other details. So we said if it passes, then you accept that step size. You accept that step, meaning that new parameter vector, WK plus 1, you say, great, that's my new parameter vector. But you also say, well, maybe my step size was too small. Maybe I should really be a bit more greedy next time. And so what you do is you increase your step size. This is the typical way it's done. You take your old step size and you multiply it by a number greater than 1, which is another design parameter. Maybe that value is 1.1. And that gives you your new step size. In this way, if your initial step size, your initial guess is too small, over time you'll just keep increasing it until it causes problems. And if there was a failed step, then you decrease it this way. You just take your old step and you multiply it by some number beta decrease that's less than 1. So this is another design parameter. Maybe you choose that as 0.5. So you gradually increase your step size, but then when it fails, you take a big change down, and then you gradually increase it and down, and it will eventually kind of figure out what is the optimal step size and sort of oscillate around it. Once in a while, you'll get a failure, meaning you've sort of wasted an iteration. But if you choose all these parameters well, then maybe that doesn't happen too often. So most of your steps are productive. Once in a while, you have an unproductive step, which helps you get the right step size.
I know you can't find it, but is there a C that, I don't know if it changed for each one, but is there a C that is perfect?
Not necessarily. It's sort of maybe early on in the optimization, there might be one C that you want, but then later, as you get close to the minimum, there's a different C, because it could be that the curvature of the cost is changing. So
every new gradient, it would be a different C.
yeah, so basically, yeah, there's sort of locally, there's maybe an optimum C, but then globally, no, there's not. And so we'll see this in an experiment, how the optimal C appears to change. I'll show you a picture in just a couple slides. Okay, but it is the overall idea making sense? Any other questions on this? Okay. Okay, so I think we've discussed everything here. So let's program this in Python. So it's not too difficult to program. Here is our for loop over our iterations. Here's our gradient step, like before. And here's the Armijo evaluation. If the new cost is less than the old cost plus here's the norm squared. Let's see. I think there should be, I don't know why there's not a, there may be a mistake in the lab. I think there should be a square on that norm. And here's our learning rate and our C. So if this passes, we accept the update. So we accept those parameters, we accept the new cost, we accept the gradient, and we change our learning rate, increase it a little bit. On the other hand, if it fails, we decrease our learning rate, and you can see we do not accept W1, we do not reset W0, J0, we keep them the same. Okay, so this is what happened if you look at the loss versus iterations and if you look at the learning rate versus iterations. So originally, we had a guess of 10e minus 3, and you can see the first thing that happened is the step was unsuccessful because as you go from iteration 1 to 2, we have the same loss, and we see that the step size actually decreased. So that first step was unsuccessful. But then, now we got it to a successful range, and you can see there's 1, 2, 3 iterations that were successful. We're gradually increasing the step size, and the cost is meanwhile decreasing. But then we had an unsuccessful step, so the cost stayed the same, and we decreased the step size here. But then we had about 70 or so successful ones where we gradually increased the cost. Gradually increased the step size, the cost kept coming down. And then we were in this region here where it's like we have a decrease and then a few increases, a decrease and a few increases. And overall, you can see that the step sizes that are working seem to be increasing as we get closer to the optimal solution. So they are, maybe the optimum step size over here is around here, but originally the optimum step size was down here. So it does change over the iterations. And we can see that we've done a pretty good job in terms of in 2,000 iterations, it does look like we have sort of settled out. There's not really much more loss to decrease. So basically, yes, this is successful. And this is the test accuracy is better than what we got before with any of our different gradient descent step sizes. So Armijo was successful in this case. Okay, so that's all I wanted to talk about today. Are there any last questions on this? All right, well, if you have any, you can ask me after class. Otherwise, see you guys on Friday.